Section 8.5 is adding and subtracting rational expressions. I can add and subtract rational expressions. That's our learning target and what we're shooting for. Big ideas in this section are: much of what is true about operating with fractions can be used in operations with rational expressions. Rational expressions can be added or subtracted by first finding a common denominator, preferably the least common multiple or the LCM of the denominators. It doesn't have to be the LCM, but that's going to make it a lot easier when we're dealing with rational expressions. When we dealt with regular fractions, it wasn't necessarily so hard at the end to simplify. With rational expressions, a lot of times it is going to be a lot more difficult to pick out those factors. So we want to use the least common multiple of the denominators or our least common denominator whenever we can. The LCM of denominators is the product of their prime factors, each raised to the greatest power that occurs in any of the expressions. To add or subtract expressions, we first need to find that common denominator. Again, that's usually the least common multiple. And that's to add or subtract any kind of fractions, whether they're rational expressions or just regular fractions. To find the LCM of several expressions, we need to factor the expressions. The LCM is the product of each of the prime factors raised to the greatest power it occurs in any of the expressions. And that sounds like a lot here, guys, but we're going to break it down here in example 1. So, finding the least common multiple here between our first term and our second here. First thing we need to do is break it down into factors. So right now, we have 12, which is 4 times 3. 4 is 2 times 2. So when I list my factors, x is already factored, y's are here. I need to factor as well. Factor that trinomial into 2 binomials. Multiply to 1, add to 2, positive 1, positive 1. Now I'm going to list my factors. I have 2 squared times 3 times x squared times y times x plus 1 squared. I want to list them there as individual factors, 2 powers if I need to. So 2 squared, x plus 1 squared. And I want each one of them to have their own column. Now I'm going to do the same thing here with my 18, 9 times 2, 3 times 3, and my trinomial here. Multiply to 4, add to 5. Positive 4, positive 1. We want these to be completely broken down into factors. As prime of factors as we can get, which means they can't be broken down any further. Their only multiples are 1 in themselves. So, I have a 2. I have 3 squared. I have an x, y cubed. I have an x plus 1. Again, I want to make sure these all go in the same columns. And I have an x plus 4. Now, those are my 2 terms here completely factored. To find my least common multiple, I look at each column and I pick the factor with the highest exponent. I have 2 squared times 3 squared times x squared times y cubed times x plus 1 squared times x plus 4. And I just have this in one column, but that's okay. Now I can simplify this a little bit. 2 squared is 4, 3 squared is 36, x squared, y cubed, x plus 1 squared, x plus 4. And this right here is my least common multiple. So up here, when I said that we take the product of each of the prime factors raised to the greatest power it occurs. What that means, guys, is that we break them down into prime factors. We multiply them all together. And we pick the ones that have the highest exponent because we need 2 to occur twice. We need 3 to occur twice because 2 occurs twice in 12 and 3 occurs twice in 18. So those have to be accounted for. Same thing with our variables and our binomials. Let's try another one here. Again, our first step is to completely factor. So I have 2x plus 2. Here I have multiply to 6, subtract to 1. Going to be 3 and 2. Since I subtracted, I need different signs. Sign in the middle always goes to my bigger number. Now, when I list these, I'm going to make sure each prime factor has its own column. I have a 2 column, an x plus 2 column in my first line. Now, for my second one here, I have an x plus 2, so I put it in the same column, and an x minus 3. To figure out my LCM, my least common multiple, I have 1, 2. I have x plus 2 twice, but only one time for each factor, which means the exponents are both 1. That's my biggest exponent. That's what I bring down. And an x minus 3. So again, it doesn't matter that that this was in both factors. That does not matter. That it was a factor of both terms does not matter. I needed just the highest exponent number of times. So since it only occurs once in each, I just bring it down once. Same idea with b here. Even though there's 3 things, we're going to do it the same way. So first we're going to completely factor. Multiply to 4, subtract to 3. 4 and 1. Different signs. Bigger number gets a sign in the middle. Multiply to 8, subtract to 2, 4, and 2. Different signs. Bigger number gets a sign in the middle. And our last one here. Multiply to 4, add to 4, 2, and 2. Same sign since we added, both negative. Now, we list them out, and each different factor gets its own column. When I go to my second term here, I have an x plus 4, so I put that in my x plus 4 column. I don't have an x minus 1, so I skip that, and I make an x minus 2 column. Now, for my last one, I have x minus 2. I have 2 of them, so it's squared. I switched from that green, it's kind of hard to look at. Okay, I have x minus 2 times x minus 2, so I have x minus 2 squared. To find my final LCM, I pick the biggest exponent for each of my factors. So if I look here, I have 1, 2, 3 columns, which means I need to have all 3 of those accounted for in my answer. In my first column, my x plus 4s, I just have 1. My biggest exponent on those is 1. I just have x minus 1 in my blue number there, and that's okay. I still just drop it down. My third column, my x minus 2, I have 2 of them, so I brought down 2. And this right here is my LCM. The LCD of rational expressions is the LCM of the denominators. So the LCD is the least common denominator, and that's just going to be the least common multiple of the denominators. Once we have the least common denominators, we write equivalent fractions and then add or subtract using the common denominator. In example 2, it says, find the sum of these 2 rational expressions in simplest form. Then state any restrictions on the variable. So again, the first thing we need to do is find that least common denominator. In order to do that, we have to factor. Multiply to 2, add to 3. It's going to be 2 and 1. Same sign since we added, they're both going to be negative. So we need to find our LCD, which is our LCM of our denominators. I have an x minus 1. I have an x minus 2 and an x minus 1. X minus 1 from here, x minus 1, x minus 2 from there. And notice even though here I have x minus 2 listed first, I listed the x minus 1 first there, so it's in the same column. My LCD then is going to be 1 of my x minus 1 factor, 1 of my x minus 2 factors. Okay, we can use our denominators here, since we've already got them factored out, to state any restrictions, just like we did yesterday. So I can state any restrictions by taking those denominators equal to 0. X cannot be 1. X minus 2 cannot be 0. So x cannot equal 2. So here's the restrictions on my domain. X can't be 1. X can't be 2. Now, before I can add my fractions, I have to get common denominators. My second fraction here already has the common denominator, my LCD, x minus 1 and x minus 2. My first fraction, though, doesn't. All it has is the x minus 1. I still need the x minus 2. So I'm going to go ahead and multiply the denominator by the x minus 2. That gives me my common denominator. I have both pieces now. But whatever I do to one part of a fraction, I've got to do to both. So if I multiply the bottom, I have to multiply the top. I'm going to distribute that and get x squared minus 2x. Over my common denominator, plus 2x minus 1 over my common denominator. Once I have a common denominator, I can add my numerators and write it over my common denominator. Again, we want this in simplest form, so go ahead and simplify your numerator. Negative 2 plus 2 is 0. And simplify again if we can. Here I have a difference of squares. X plus 1, x minus 1. Over my x minus 2, x minus 1. Last step here is anytime we have something divided by itself, it cancels out. So my final answer is going to be x plus 1 over x minus 2 with my restricted domain, as long as x is not 1 or 2. I'm going to stop this video here, and we'll start with the extra examples for problem 2 here on the next video.